So a machine like this has three basic components. It has a block here, a block there, and it has a string wrapped around the pulley. So when we're done, we need to compare all of the forces acting on each of the components of this particular machine, and we need to determine the net acceleration and the forces acting on all the objects involved. So the first thing we're going to look at is that there's a 20 kilogram object up in the air and there's a 15 kilogram object down on the ground. Now just logically, the 20 is going to fall, the 15 is going to rise upwards. So we just have to figure out at what rate. Alright, so if I look at this then, there are a few forces involved. First off is going to be force of gravity acting on block 1. So force of gravity acting on the 20. There's going to be a force of gravity acting on the 15. And because there's a string involved, there's going to be a force of tension that we have to calculate. So I'll just pop that up there, tension. Alright, so when you calculate force of gravity, there's just that formula for it. So the force of gravity would be the mass multiplied by the acceleration. Right? That's how we've been calculating forces. And if you're something falling under the influence of gravity, there's a very specific acceleration that you use. It's not just A, we can use G, where G is 9.8 meters per second squared. So I'm going to take this number, I'm going to park it in here, and I'm going to calculate this force for the 20 kilogram block, and I'm going to calculate it for the 15 kilogram block. So let's see. For the 20, the force of gravity would be 20 kilograms multiplied by 9.8, and I get 196, I think. 20 times 9.8. Yep. 196 newtons. And for the 10, the force of gravity would be 10 times 9.8 for a total of, oh, it's not 10 kilograms, goofball, it's 15 kilograms. We'll get this right eventually. So 15 times 9.8, it's 147. All right, so I can start filling this stuff in. 196 newtons here, 147 newtons here, and I'm not sure about this one quite yet. So what I can do at this point is start asking which direction all these forces are going to be pointing. So if I, well, no, let's not do it that way. Let's erase this. As far as the tension force goes, the way tension works in the string is whatever strength it's pulling at this way, it has to also be pulling from the other direction, right? You can't hold a string tight and have it be tight on the left side and loose on the right. That is not how strings work. So on this block then, the tension in this string is what's going to end up lifting that one. And the tension in this string is what's holding this one back. So this one doesn't get to free fall because the tension in the rope is pulling back on it. This one doesn't get to sit on the ground all day because the tension is going to lift it. And the tension is generated, of course, by the fact that these two masses are trying to do something else. So if I were to think about what's happening to this block in total, so that means that I'm going to go through and I'm going to calculate a net force. Well, first thing I'm going to find is that there is a force of gravity from the 20 kilogram block. So that's this one. Then I have a force of tension here on one end of the string. And then I have another force of tension here on this side of the string. And then I have a force of gravity from the 15 kilogram block. All right, now, here's where things get a little tricky. If you were to look at that machine and decide which way it was going to go in the first place, I think we can pretty much agree that the 20 is going to fall and the 15 is going to rise. So I need to go through each of these forces and I need to decide which ones are helping the 20 to fall or helping the 15 to rise, and which ones are preventing the 20 from falling and preventing the 15 from rising. So the natural action for this would be to turn clockwise. So which of these things are making them go clockwise? Well, this one, the gravity pulling down, that's positive. That's helping. This tension here, that's pulling backwards on the 20. So it's trying to pull this thing counterclockwise. So it's going the wrong way. This tension is trying to help the 15. So it's a positive. This gravity is pulling backwards on the natural motion. So it's negative. So I have my expression for the net force. All four forces acting on that machine are accounted for. Some of them are positive, some of them are negative, depending on which way they're oriented. And I just have to calculate my net force now. So the handy thing about these two is that it doesn't matter how big they are. Ft minus Ft just drops out of my equation. So I'm only left with these two terms. So net force would be, the force of gravity from the 20 kilogram object is 196 newtons. And the force of gravity from the 15 kilogram block is 147 newtons. And if I work that out, 196 minus 147 gives me 49 newtons. So my net force is 49 newtons. Once I have a net force, I can make the replacement here for force net to mass net times acceleration net. Right, that's just a generic thing for forces. That's equal to 49. So if I could figure out how much mass is being moved in total, then I could figure out how this system would accelerate under this much of a force imbalance. So my net mass then, this force here, this 49 newtons, has to accelerate the 20 kilogram block and the 15, because both of them are going to move, and they're locked together on a string, so they have to accelerate at the same rate. So my net force then would be this 20 plus the 15. My net acceleration is 49. So that's 35. And to finish, I just need to divide both sides by 35. Which is approximately 1.4 meters per second squared. So I have an acceleration of 1.4 meters per second squared. Excellent. Now, we've done a lot of work here and we figured out what the acceleration of the system is, but there's this one pesky thing that we don't have an answer for. I don't know what the tension is. So I'm going to have to erase this to get us some space. So I'm going to do that now. So the trick about tension that really befuddles a lot of people is there isn't a formula for it. You have to determine it based on the situation. So I'm going to pick a block. I'm just going to pick the 20 because it's the one up in the air. So here's my 20 kilogram block. Now what I just figured out was that it had a force of gravity acting on it of 196 newtons. And I've also learned that this block, once I let this thing roll, starts to accelerate at 1.4 meters per second squared. And if I look at just the 20, ignoring the thing on the left, I can see that there is a force of tension that is reducing the acceleration of this block. If not for this tension force, this acceleration should be 9.8. But this thing's slowing her down. Now, if I consider just this system, what I can see is that the net force would be the gravity subtract the force of tension. So this is trying to make the thing go in the direction it's going to go, and this is resisting, so it has a negative attached. Unlike the last question we did, where we knew all the forces but not the acceleration, this one's a little backwards. Now I know how it accelerates, and I'm trying to calculate this thing here. So my M net, A net here, the mass of this is 20, and it's accelerating at 1.4. Notice that all the numbers are filled in except that force of tension. So 20 times 1.4 gives me 28. And if I kick this to the other side, (28 minus 196) gives me negative 168. And if negative force of tension is negative 178, then the force of tension must be 168 newtons. We can pop that in there. So as long as you have a rope that can tolerate 168 newtons worth of tension, then I can use it to operate this machine, which will allow a 20 kilogram block to accelerate a 15 kilogram block like so at a rate of 1.4 meters per second squared. So if I take a machine like this and I add in the extra detail that I know that the hanging block starts 6 meters up in the air, then I'm going to be able to work with some energies here in order to determine the final speed of the block when it reaches the ground. We'll be able to use some kinematics in order to figure out the time that it takes in order for it to achieve this. So when we look at it, we have 2 blocks that are hanging. So I'll need 2 gravities. I have a string, which means I need a tension. I'll be able to use these forces to get an acceleration. And then I should be able to use the energies involved to get the final speed. I can use the final speed of whatever I calculate, the initial speed of 0, and my acceleration to calculate the time. I also have distance, so I could use that as well. There's a lot of work to do here in order to analyze it, but at the end, I should be able to tell you everything that this machine is capable of doing. So let's get started. Forces of gravity first. They're always easy, so you should do them. Grease in this marker. Force of gravity for the 23 and force of gravity for the 86. So FG's for 23 would be 23 times 9.8, which gives me 23 times 9.8. 225.4.
Mr. Perry, please call 527. Mr. Perry, 527, please.
And the force of gravity for the 86 kilogram block would be 86 times 9.8. 6 times 9.8 is 842.8. So I have 842.8 newtons. Now if I were to work out a net force for this particular thing, force net should be the force of gravity from the 86 kilogram block minus the force of tension in the string, because it's pulling back, plus the force of tension in the string because it's lifting the 23 kilograms, and then minus the force of gravity from the 23 because it is resisting all this action. As in the last example, these two things, because they're equal size but opposite directions, end up going away. So my net force then would be the force of gravity from my 86 kilogram block, 842.8, minus 225.4, for a total of 225.4, 617.4. And force net is a mass net times an acceleration net. So my net mass then would be this 23 plus the 86, because both of them have to move. So that would be a total of 109. So divide both sides by 109. .4 divided by 109 is 5.664. All right. There we go. So in order to do tension, I'm going to isolate one block and just work on the forces acting on it. In the last example, I used the hanging block. So just to show you that it works for either one, I'm going to use the sitting block as this for my tension this time. Right, so this 23 kilogram object has a downward force of 225.4. It has an upwards acceleration of 5.664, and it's being provided by some force of tension. So if I look at that, then the net mass times the net acceleration should be this force of tension, because it's the one that's winning, subtract this force of gravity. That's what's holding it back. So my net mass, if I've isolated just this side, is 23 kilograms. The acceleration is 5.664. Force of tension minus 225.4. So that number, that acceleration, times 23 is 130.277. And if I pop this over to the other side, I'm adding 225.4. So my force of tension is those two added together plus 225.4 gives me 355.667. Sorry, 677 newtons. Now, it's always a good idea to check. This tension can't be bigger than the force of gravity acting on the 86 kilogram block. If it were, then this one wouldn't be able to fall. So you check. 355 is less than 842, no problem. So this thing is going to be able to spin in that direction. All right, so now that we've done that, I have an initial speed, which is 0, the thing starts up there. I have a distance of 6, and I have an acceleration of 5.664. That means I can calculate the time it takes for this event to happen, for this block to reach the ground. I can also calculate the final speed. So I'm going to do those things once I clear some space. All right, so if we do the VI, D, and A, let's do V final. So V final squared minus V initial squared is 2AD. V final I don't know. V initial was 0. The acceleration is 5.664 in this direction. And the distance is 6 meters. Now, if you wanted to call this negative 6 meters because it's dropping, that would be okay. Then you'd have to use negative 5.664 because it's accelerating in that direction. I'm choosing just to leave them out because it doesn't make it any clearer, I think. So Vs squared is 2 times 5.664 times 6 would be 67.968. So I need to square root that. Which gives me 8.244. Now, consequences. If I chose this way, 6 meters this way to be positive, with an acceleration going this way that's positive, then the V final should be going this way, which is positive. That's what I've chosen. So choose positive by context. Therefore, the final speed is 8.244 meters per second. I have a final speed now, so I can use that with my acceleration and my initial speed to calculate time, thus dodging the quadratic formula. So Vf minus Vi is At. V final was 8.244. The initial was 0. Acceleration of 5.664 t. So I'm going to end up with 8.244 divided by 5.664 to give me my time. Time will be 0.244 divided by 5.664 is 1.456 seconds. So I have a time here, 1.456 seconds, and I have a final speed of 8.244 meters per second. All right. So the last thing to ask yourself is how much energy was available to run this machine in the first place? And then let's account for all of it to make sure that we know where everything is. Okay, so at the beginning, this block was not in motion and it was on the ground. So it had 0 kinetic energy and it had 0 gravitational potential. Also at the beginning, this object was not in motion. So it had 0 kinetic energy, but it was 6 meters up in the air. That means it was full of gravitational potential energy. So the energy to run this machine was stored entirely in this block. So we're going to calculate how much that was by doing the gravitational potential energy equals mgh of this 86 kilogram block. So that's 86 kilograms, g is 9.8, and we're 6 meters up. So 86 times 9.8 times 6 gives me 5,056.8 joules. So when I'm done, I should be able to account for all 5,056.8 joules. Let's try that. Energy at the end. Well, first off, this block at the end is sitting on the ground. So it has no gravitational potential energy left. But it is traveling at 8.244 meters per second. So in the 86 kilogram block, it's going to have some kinetic energy, 1/2 mv squared. So that will be 1/2 of its 86 kilograms multiplied by its final speed of 8.244. Giving us a grand total of 86 divided by 2 times 8.244 squared gives me 2,922.432. Okay, so you notice that this is not all of that. It's most of it, but it's not all of it. At the end of this system, so when this one finally clunks on the ground, this block will be up in the air. Because the string is attached to it, whatever this drops, this must rise. So this block will be 6 meters up, which gives it some gravitational potential. So for the 23 kilogram block, there will be some gravitational potential, mgh. That's 23 kilograms times 9.8 times the 6 meters it has to rise. So 23 times 9.8 times 6 is 1,352.4. Now, this block will also be on the move. If this one has reached a speed of 8.244, then this one must also have reached a speed of 8.244 because they're connected, right? They're coupled by that string. So the kinetic energy for this block, EK, be 1/2 mv squared. 1/2 of its 23 kilograms multiplied by this final speed of 8.244 squared. So 23 divided by 2 times 8.244 squared gives me 781.581. All right. So this amount of energy at the beginning, allegedly, was able to make this machine work. When this machine works, it has to have given this object kinetic energy. It has to have given this object some gravitational potential because it lifted her up. and it must have given this object some kinetic energy because it is also in motion. So if everything has worked out, this energy plus this energy plus this energy should account for all of this 5056.8. So we're going to try that. 2,922.432 joules plus 1,352.4 gives me, so far I'm at 4,274.83, plus this energy down here, 781.581, gives me a grand total of 5,056.413 joules in total. So I will assume that within a rounding error, we have accounted for all of the energy that we had at the beginning. So this machine had the following forces of gravity. The string is under this much tension. The system will accelerate at that rate. It will take exactly this amount of time in order for the blocks to switch places. The final speed of the two blocks is 8.244 meters per second. There was 5,056.8 joules available at the beginning to power this machine, and we have discovered exactly how it's allocated when the machine has done its work.
Mr. Fraser, call 524, please. Mr. Fraser, call 524.
Now, that is not a very complicated machine, but what's neat about this is you know everything about it. And if you can know everything about a machine, well, that's when you can start tweaking it and start manipulating the outcomes or start using it for something handy. So we're going to go on to the next more complicated one, but just take a minute to appreciate knowing everything about a situation. It may never happen to you again. In a machine like this one, where there's one hanging block and another block resting on a table connected by a pulley, there are four forces acting. There's first off a force of gravity from the block that's hanging. So there's a force of gravity on the 8 kilogram block. There's a force of gravity acting on the 20 kilogram block. There's a force of tension because there's a string involved. And the final one is a force of friction between the 20 kilogram block and the table. Force of friction. All right. So when you do any question like this, the easy two to get are the forces of gravity because they're always the mass times 9.8. So for the 8 kilogram, force of gravity would be 8 times 9.8, giving us a total of 78.4 newtons. For the 20 kilogram block, force of gravity would be 20 kilograms multiplied by 9.8, which I think was 196. Indeed. Now, when we get to these two, if you recall from the last question, I was not able to calculate a force of tension unless I knew that this thing was, how it was accelerating. So I'm going to add a little piece of information for you. I'm going to suggest that this machine is stuck. So if we do that, if I were to draw just this 8 kilogram block then, 8 kilograms, we already calculated here that there was a force of 78.4 newtons pulling that way. Now, if this thing is stuck, right, that this is not able to slide, this is not able to fall, right? There, it's locked unless the string breaks. So if this block is not falling, there must be a force available in order to balance this. And the only thing I have on there is this string. So in order for this string to be balancing the force of gravity, the force of tension in it must be 78.4 newtons. So situationally, I could look at how this machine was operating, or not operating, as it were, and I can just park in that force of tension. Now, if I look up at the 20 kilogram block sitting on the table, it has a string attached to it pointing this way. And as we said in the last example, if you have a string under tension at this end, it's under identical tension at the other. So if it's 78.4 newtons pulling on this side, then it must be 78.4 newtons on this side pulling that way. So if the machine is stuck, there must be something pulling back on this in this direction. And the only thing we haven't talked about yet is this force of friction. So there must be a force of friction pointing backwards on this particular object. And I can tell you that in order to balance this 78.4, this force of friction has to be exactly the same size in order to make it stuck. So that's interesting. Is it? Obviously, if the machine is stuck, there must be a way of calculating friction other than doing it circumstantially like this, and in fact there is. In order to do a force of friction, you need two things. You need to know how sticky the two surfaces are. So, for example, steel on steel is not very sticky, which is why train tracks are made that way. Rubber on asphalt is very sticky, which is what makes cars work the way they do. Rubber tires on ice is not very sticky, so we need some sort of number to represent that. And the thing that goes in here is a Greek symbol. It looks like that. It kind of looks like an M. It kind of looks like a U, and then that's its name. It's a mu. It's a Greek letter. And that mu is standing for the coefficient of static friction. So let me write that down here. Mu is the coefficient of static friction. All right. So that's the first thing we need. The second thing we need to know is how hard those objects are being pressed together. And if I'm a 20 kilogram block sitting on a table, the force that's holding me to the table is the force of gravity. So in this, I'm going to put in this thing here, Fn, F normal, which is how hard the things are being pressed together. In this case, normal force is the table pressing back on the 20 kilogram block, which is balancing out the gravity from the block trying to go through. So for this particular calculation, my friction then will be some coefficient of friction multiplied by the gravity acting on the 20 kilogram block. Well, I know that this is 78.4 newtons. I don't know this, but I do know that the gravity acting on the 20 kilogram block was 196 newtons. So I could finish this calculation by dividing both sides by 196. And I get a mu value of 78.4 divided by 196 is 0.4. There you go. So if this machine is stuck,
Mr. Perry, please call 527. Mr. Perry, call 527.
there must be 78.4 newtons hanging because of gravity hanging on this, which makes a tension force of 78.4 newtons, which requires a friction force of 78.4 newtons to hold the thing still, meaning that the coefficient of static friction between the block and the table must be equal to 0.4. Alright, so for these two blocks sitting on the table, note that it does not say that the system is stuck. What it does say is that there is a coefficient of static friction that I know about. So I'm going to be able to calculate the force of friction in this particular question, and because I can do that, I'll be able to determine how this thing accelerates, if it accelerates. So looking at this particular machine, I can see that there's going to be a force of gravity from this. There'll be a force of gravity acting on this, which is going to press against the table, causing a force of friction. And there's going to be a force of tension because of the string. So I have four forces to work out. I can also see that the only source of energy I have is this particular block hanging above the ground. So whatever energy gets consumed by this particular process has to have come from the gravitational potential energy of that block being up in the air. So there's a lot of analysis to do on this. So as we start with gravities, as always, so the force of gravity for the 8 kilogram block will be 8 times 9.8 for a total of 78.4 newtons. I have the force of gravity acting on the 30 kilogram block to be 30 kilograms multiplied by 9.8. 30 times 9.8 to be 294 newtons. Now this is new. I have a force of friction that I can calculate. So force of friction is the mu multiplied by the force squashing the two objects together. So that's normal force. Because this thing is flat, the tendency of the table to push directly up onto the block is the same force as the gravity pulling down on the block. So I'm going to be able to use the gravity of my 30 kilogram block for the force holding me together. And I'm going to be able to use 0.2 as my coefficient of static friction. 0.2 times 294 gives me a total of 294, 58.8 newtons. All right, so in order to do a net force then, I'm going to ask myself, if this thing moves, will it go this way or will it go that way? And there's nothing causing this block to slide to the left. But there is something trying to pull this block down, right? That's gravity. So if I take all of these forces then, the 78.4 newtons from the force of gravity on the 8 kilogram block, that's pulling this way. And then there is a force of tension pulling in the wrong direction. And then a force of tension encouraging the 30 kilogram block to move. And then there's a force of friction fighting the entire action. So there are my four forces accounted for. So in my net force, the numbers I will need is the gravity of the 8 kilogram block, that's here, 78.4. These two things, I mean, this is very familiar. They're the same size in opposite directions, so they end up undoing each other. And from this pile, I have to subtract the force of friction acting on the 30 kilogram block. So that's this. So my F net in total then would be 78.4 minus 58.8, which is 19.6 newtons. So I have an F net of 19.6. Okay, so F net is mass net times net acceleration. So the net mass here, both the 30 and the 8 must be moved. So that's 38 kilograms are being accelerated by this 19.6 newtons. So to get my acceleration, I will have to divide this by 38. This gives me a total acceleration of 0.516 meters per second squared. All right. So I have an initial speed of 0 because the block is initially hanging there. It passes through 0.9 meters worth of space and it accelerates at this rate. That means I have enough information to do a kinematics calculation to calculate the time it takes for it to fall and the final speed when we get there. So I'm going to do that. So final speed I don't know. Initial speed was 0, 2 times an acceleration of 0.516 passing through 0.9 meters. Again, I'm going to choose this way as the positive direction because the machine will roll that way. So Vf squared is that acceleration times 2 times 0.9 gives me 0.928, and I will have to square root that. And I get 0.964 meters per second. All right, so this block will be dropping at 0.964 meters per second the instant it hits the ground. And this block will be sliding that way at 0.964 meters per second the instant this one hits the ground. So I have a V final. Now note, I chose positive by context. Okay, so now I need to get my time value. So Vf minus Vi is AT. So 0.964 minus nothing is my acceleration of 0.516 multiplied by the time. So 0.964, divide both sides by this, gives me my time value for a grand total of 0.964 divided by 0.516 is 1.868 seconds. All right, so time value 1.868 seconds. Lovely. So last thing to do is to go through and do the analysis on how much energy was available to run the machine and how much energy is accounted for at each stage. So just like the simple pulley machine, this particular block is the only one who has a compulsion to move. So its gravitational potential energy is the only energy we have to run this machine. So its gravitational potential is mgh. That's the 8 kilograms times 9.8 times a height of 0.9 for a total of 8 times 9.8 times 0.9 gives me 70.56 joules, which is considerably less than the last machine we had. But I mean, these accelerations are much lower, final speeds are much lower. Also, the other one was an 86 kilogram block, which is about person size, lifting 23 kilograms, which is about a dog. So if you can imagine tying yourself to your dog over a pulley and then stepping off a table, that's going to be real aggressive and real messy for everyone involved. Don't try this at home. So I should be able to go through this, and I should be able to account for all of this energy there. So let's think about what these blocks are doing at the end. So energy at end. When this is done, this 8 kilogram block will be resting on the ground. So it will have no gravitational potential energy. This 8 kilogram block will be traveling at 0.964 meters per second though, so it will have kinetic energy. So we should get that. So for the 8 kilogram block, EK is 1/2 mv squared. It's 1/2 of its 8 kilograms multiplied by 0.964 squared. 1/2 of 8 times 0.964 squared gives me 3.717 joules. It's not very much. Now this block here, it had some gravitational potential because it's sitting on the table, but if it's only sliding horizontally, all of that energy is still there. So we didn't have to account for that. This block will be traveling that way with some speed, so I need to find its kinetic energy. So for the 30 kilogram block, EK is 1/2 mv squared. So that will be 1/2 of its 30 kilograms multiplied by this silly speed of 0.964. Alright, so 30 divided by 2 times 0.964 squared gives me 13.939 joules. Alright, now we're supposed to have added up to 70.56, and I only have this energy from the 8 kilogram block. It's like about 4 joules, and this is about 14. So we've got about 18, which means we're like 52 joules short. So where did it go? Well, the only thing we haven't accounted for is the fact that this block was experiencing some friction. And if you don't want to just trust me on this, if you take two objects and you move them against each other, they start to heat up. So whenever you have friction drag between two objects, you are shedding some of our initial energy as heat. So it's waste, basically, from this machine. So how much waste is it? Well, we're going to fall back on an idea that the amount of energy you get out of something is the force you're experiencing multiplied by the distance that you go through. This is a concept called work. And usually there's a W there, but I'm just going to use an E because that's really what we're talking about. So if I'm talking about the heat loss here, EH for heat, I'm going to have to take the force of friction multiplied by the distance that that block passed through. So in this case, the friction between the 30 kilogram block and the top of the table was 58.8 newtons. And if this block dropped 0.9 meters, then this block dragged 0.9 meters. So it passed through 0.9, which gives us a total of 58.8 times 0.9 is 52.92 joules. So if I were to go through my list here, I have this much kinetic energy, this much kinetic energy, and this much heat loss. So if I were to add them up, 52.92 plus 13.939 gives me 66.86 plus 3.717 gives me 70.576 joules. And that's what I had within a rounding error. So I took this machine and I figured out the size of the gravities acting on both parts. I discovered the friction that was acting on the tabletop between the 30 kilogram block. I've learned all of its kinematics variables, so I know exactly how it's going to behave. I know I had 70.56 joules to spend in the first place, and what I got out of it was 3.7 joules of kinetic energy on this block, 13.9 joules of kinetic energy on that block, and a whopping 52.92 joules of heat waste acting between the table and the dragging block. So you can see why when you're trying to get things to slide, like pistons inside of an engine block, or like the wheels on a shopping cart, right? Friction is a real energy sucker. So if you can do anything to minimize this static coefficient by using a lubricant like an oil, or ball bearings, something that rolls more easily than the wheel might naturally, then you can reduce this heat waste and get more kinetic energy out of it. Now as I'm looking at this, there's one more force I'm missing. Can you guess what it is? Well, it's the tension in the string. Of course, we don't have that yet, so we'll finish off by calculating that force. So if I isolate the 8 kilogram block, and I look at the force of gravity acting on it, so the 8 kilogram block's force was 78.4 newtons. And the thing is accelerating downwards at this particular rate, 0.516 meters per second squared. If there were nothing else attached to it, it would be accelerating at 9.8, but there is this pesky string attached here, providing a force of tension. So if I were to look at how this is arranged, my net force should be this 78.4 subtract whatever this tension is providing. Because the thing is going down, which means this is winning, and this is providing some resistance. So I put the winner there, subtract whoever's fighting back. I happen to know the acceleration, and I happen to know the mass. So I can write this as the mass multiplied by the acceleration. Eight times 0.516 is 4.128 I'm going to have to subtract this from both sides. Let's get it over there. 4.128 minus 78.4 is negative 74.272. So the force of tension then must be 74.272 newtons. And there you go, you know everything about every component in this machine, including the fact that there's 74.272 newtons of tension in the rope.